Say this is our circuit. Let's start by drawing all the nodes at which we're going to have nodal voltages. So you can have nodes anywhere in the junctions. So one here, one here, one here. We're not gonna be having one here, but we're gonna be having one here. Same thing, since this one 0, this one 0, since it's on the same line. But these ones aren't gonna be 0. And also, since we're using force current analogy, it's also going to be useful to have a node, if I can call it that, in between the two components in series. You know, two components in series, they're going to have the same current, but they're going to have a different voltage. So the resistor and the inductance are going to have different voltages. So this one has a voltage, this one has a different voltage, and this one will have a different voltage. These ones are 0, the last two. Okay, so that's that. We're doing force current analogy. So the sum of currents is going to have to equal 0 for each free node. For node 1, for node 2, and for node 3. So we want to write everything in terms of current, I. You know that V equals IR, so voltage is current times resistance. And if we want to write it in terms of current, you can write that the current is the voltage over resistance, or E over R. You can write voltage as E, little e. Okay, so now looking at our nodes, we need to label them in green. So this is going to be E1, voltage at node 1, voltage at node 2, voltage at node 3. This one is just 0, so you don't care about them, because it's grounded, you can see here, so, 0. Okay, so we wrote down the voltages. What is the voltage going to be equal to from E1 to E2? Since we're in series for this part, for this whole segment, you know that E1 has to be E2 plus the voltage across the resistor. So E1 is the voltage across the resistor plus the voltage at 2. And in terms of I, since that's what we're doing, we're writing everything in terms of I, the current through the resistor is going to be the voltage, ER, over the resistor. So ER over R1, resistor 1. You know that ER, you can write in terms of these two. So ER is going to be E1 minus E2. ER is E1 minus E2 over R1. So that's that for the first one. But we're talking about the sum. So going back to pink and writing the sum, you have the current coming in from the source, so IA, and from the source, next up would be the consumer. The resistor is your consumer. So you would have to, ignore this for now, so starting from IA, you would have to subtract whatever voltage drop you have because of the resistor. So that would be this current. From the source, IA, you subtract the current here. So minus IA, you have minus E1 minus E2 over R1. This is in brackets. But we want to write the sum of voltage in node 1 as equal to 0. So rearranging this now to equal 0, you can write IA plus this time, and then just inverse whatever voltages you have in the bracket over R1. So that's for the first one. Next up, the sum of the current in node 2, V2, E2, same thing. Once again, this has to equal 0. What do we have going on? Which one's our consumer and which one's our source? Our source this time would be the resistor, R1, and the consumer would be the inductance. So the source from E1 to E2 and the consumer from E2 to E3. So how do we write the current from the source, R1? We already know the current from the source as this. So we can write it here. The current from the source is E1 minus E2 over R. From which you would have to, if we ignore the fact that it equals 0, from which you would have to subtract the consumer from the source. Now, for the consumer, what's going on? We're going to be writing L, inductance, as 1 over L, since its mechanical equivalent would be K. Because L, inductance, in mechanical equivalent is 1 over K. So if we want 1 over L in terms of K, so 1 over L, this, we then have to integrate, because when you integrate voltage, you're going to get current if you integrate. If you differentiate current, di over thingy. So what's going on in the consumer? You have E3 and E2. So now let's write in terms of V equals IR, voltage, writing in terms of current, so voltage over resistance. But in this case, we don't have a resistance, we have an inductance. So you can write it as 1 over L outside the bracket, which is a constant, and then integrate the voltage to get current. So that's what we're going to do. And what is the value of V that we're going to have here? E2 is E3 plus E through the inductor, so EL. So in this case, EL is going to be E2 from the source minus E3 by the time it passes through it. So here, we're going to be writing E2 minus E3. So what was that? E2 minus E3, and then dt because we're integrating. Okay, so this would have to equal 0. Now, if we want to write it with a plus sign, you could get E1 minus E2 over R plus 1 over L, integrate, and just inverse whatever you have in the brackets when you're changing the sign. So E3 minus E2 with respect to dt equals 0 equals the sum of current at node 2. Okay, now last one. Let me delete this. So what's going on? Same thing, sum of current at node V3, E3, same thing. has to equal 0. What's going on? Which one's our source? Which one's our consumer? Our source is the inductance, and the consumer is the resistor 2 and capacitor, which are connected in parallel. This one would also be a source, but right now, just looking at node 3, just take this one as your source. It's only an assumption that it's our source. It's not technically our source. We're just assuming it to be our source for the sake of the calculations. So we already know what is going on in the source. We found that previously in the second node. So that's 1 over L. Integrate the voltage to get current VT, from which we have to subtract our consumers. And our consumers are these two. How do we write resistance in terms of current? V equals IR. I is V over R. And the V, the voltage, that is corresponds to our resistance. If we write it like this, E3 is the current through, is the voltage through the resistor, plus the voltage through the, which is the same voltage as the voltage through the capacitor, plus 0, because we have 0 voltage at this node. So basically, you can just say E3 is E through the resistor 2, and E3 is also E through the capacitor. What did we write previously? V equals IR, because we're writing in terms of current, equals V over R. So our value of V, which is the same as E, voltage, you can just write as E3 over R. And from the source, we're subtracting this consumer. So minus E3 over R2. That's one consumer. We have another consumer, the capacitor. So we're going to subtract the capacitor minus capacitor. And to get current, we have to, this time, differentiate the voltage when you divide by dt.